Hey guys, I wanted to revisit the first day of alternating series notes. Now that we're using Desmos, I just wanted to make sure that you've seen how to do this in Desmos and give you another visual for what this alternating series remainder represents. First off, we can approximate a sum by using any number of terms that we decide or that they tell us. So I can say, well, the actual infinite sum of this series could be approximated by adding the first six terms together. So you can see I'm doing that with like 1 over 1 factorial. And this is really easy to do in Desmos. Let me split my screen here. Ignore this stuff for a minute. So I can say like 1 over 1 factorial. I'm not going to type that out. Minus 1 over 2 factorial plus 1 over 3 factorial. So anyway, this is, I think, a little easier to type out than it is in the calculator. So that's nice. Make sure that you are typing it in correctly, whether you're in the calculator or not. And so you can see I get this approximate value that I had on the calculator. And again, this is an approximation. So the question is, how far off is this from whatever the actual infinite sum is? And so that's where this alternating series remainder comes into play. I gave you kind of I think in the other video, there's sort of an explanation that I've seen before of like, every time we add and subtract the term, we get a little closer. And so how far off are we? Well, we're as far off as the next term would get us, because it would get us closer to the sum. But I've kind of made this visual here of, in Desmos, of kind of what we're doing. So let's take a look at this. All right, so I took the series, the infinite series that we have in the paper, and I can't put infinity in here and have it graph. So I just put a very large number, add the terms from 1 to 10 to the 7th. I bet that is pretty close to, I bet this is pretty close to the actual sum of the series. It's still going to be off a little bit, but it's going to be accurate to a lot of decimal places. And then we're going to let this y1 be a partial sum. So we could use the first partial sum. We just use the first term. We get a sum of 1. We know that's off. The alternating remainder theorem says that we should only be off by 1 over, in this case, 1 over 2 factorial, which gives us 1/2. So here's our approximation. Our approximation is at 1. And we're saying, okay, if you add or subtract 1/2 to that approximation, the actual sum should fall somewhere in there. So this 1/2 is like a maximum error. I know I'm not off by more than that. And if I, instead of using just one term, if I add the first 2 terms and use that as my approximation, the approximation you can see is closer to the actual sum. So the star is the approximation. It's much better. And I have less of an error. Now the error is only 1 over 3 factorial and plus 1 factorial. So you can see, still adding that smaller error, I'm still capturing what the true sum of the series is. And so if I do that, I keep getting closer and closer. Now I'm going to have to zoom in for you to be able to really see what's happening here. But you can see that, yeah, we are still capturing with each one the actual sum, and we get closer and closer. And so we were supposed to go out to 5 and 6. Instead of zooming visually here, I'm going to extend this table out. So here's what the true f of x is supposed to add up to. And if I take my approximation, my 6th partial sum, and I add or subtract the alternating series remainder, you can see what bounds you fall within. And look how accurate this is. We are accurate to, looks like, depending on which one we use, we could match at 3 decimal places. This would round up to matching at 3 decimal places, but the first 2 are accurate. And you can just keep going. If you keep adding terms, you get better and better. Take a look at your approximation versus what the actual is. And you can see as I add more terms, it starts matching pretty closely. The first 4 decimal places match. Now it's 1, 2, 3, 4, 5. The first 5 match. No, 6 to the 0. So it's pretty cool. Some of our questions will be, well, how many terms do you need to be a certain accuracy? The first 3 matching or the first 2 matching or whatever. So we can go through how to solve that too. Okay, so this is just what the alternating series remainder is, just giving you this maximum bound. It's showing you, well, this is the max possible error. It's not going to tell us what the actual sum is. It's just going to say it's got to fall within this range. Okay, so back to our notes here. What if I'm given a certain margin of error and I have to find that value? So let me rework my work a little bit here. Because again, I used to use the table in the TI calculator, and this is, it's a lot easier to set this up otherwise. So let me explain this again. So this time we don't know how many terms we're going to find. To determine the number of terms required to make this series be within the actual sum by 0.001. So I always set it up like this. The error between the actual sum and my nth partial sum should equal the remainder at some n value. I want that to be less, well, that number will be less than or equal to a sub n plus 1, and I want that to come out less than 0.001. All right, now this could be a calculator or a non-calculator problem, so I'm going to show you both ways to do this. So think about, and this is an absolute value, by the way. So think about what this means, a sub n plus 1. That means plug n plus 1 into this formula, and because it's an absolute value, we get to ignore the negative 1 to the n plus 1. So just make it 1 over, instead of n plus 1, instead of times 4 to the n, times 4 to the n plus 1. And if I'm doing this, actually either way, if I'm doing this calculator or non, it's helpful sometimes to change this to a fraction, so 1 over 1,000. But if you get to use a calculator, it doesn't quite matter. And so at this point, you can either type in this function into Desmos, I'll show you this in a minute, and start plugging in n's until you get something smaller than 0.001. Or sometimes it's nice to cross multiply 1,000 over to this side. That would still be less than this side, n plus 1 times 4 to the n plus 1. And then again, start plugging in n's until you get a number bigger than 1,000. This is what I would do if it's non-calculator, because if it's non-calculator, n is not going to be like 7 or something. It's going to be like 2 or 3. So we can kind of quickly go through that and say, okay, what if n is, let's say n is 2. That would give me 3 times 4 to the third, 3 times 64. I don't have to fully do the math. Is that going to be bigger than 1,000? No. 3 times 60 is 180, right? So that's not going to get me close. So what if n is 3? Never jump too far. Just go to the next one. So then this becomes 3 plus 1 is 4. This becomes 4 to the fourth. So 4 times 4 to the fourth, well, 4 to the third is 64. Multiply that by 4. That's 256. And this is going to get me close, right? I should actually multiply this out, but I'm just approximating here. Like 4 times 300 is 1,200. 4 times 200 is 800. So I might exceed 1,000. So let's multiply this. 4 times 6 is 24. 4 times 5 plus 2 is 22. 4 times 2 is 8. Carry the 2. 10. So yeah, 1,024. So we do get, when n is 3, when n equals 3 terms, so a third partial sum will add up the first 3 terms, we will be within the actual sum, within 0.001 units. Now, what if it is calculator allowed? So you don't want to type the n's in. Instead, and again, ignore, well, we already did that table there. So just want to get this out of the way. Okay, so use x's. So I want to compare this to 1,000. So I'm not going to type in n plus 1. I would just say, let's say, call it f of x. I like to default to that. Equals x plus 1 times 4 to the, you need parentheses around x plus 1 in the exponent. Otherwise, it'll always drop the plus 1 down. And then you can I just start like, okay, what's f of 1? Oh, sorry, I have too many f's. I have an f defined earlier, so I'm going to make it g. That would not be an issue unless you used f of x earlier. Okay, what's g of 1? 32. Is that bigger than 1,000? No. What about 2? 192. What about 3? 1,024. So that's a much faster way if I'm allowed to use a calculator to get there. You could have also said 1 over that, so before you multiplied, and now you're trying to compare to something that's less than 0.001. So again, you could go through the list. That's not less than 0.001. Neither is that. This is, don't worry about rounding, 0.000 is less than 0.001, right? This is less than this. You're not thinking about rounding. This exact decimal carried all the way out is less than that. All right, so I know that is a recap of yesterday, but I think this can be a little foggy, and we will be talking about error a lot toward the end of this chapter here, so this is good. Okay, so then what about the day 2 notes? As we're looking at the alternating series test, here we go. We also we will be asked if a series converges absolutely or conditionally. So here's a theorem. If a positive series converges, then a series that's not necessarily positive also converges. This usually means if a non-alternating series converges, then the alternating series converges. But it doesn't have to be alternating. We're going to see this on something that's not quite alternating further down. So it could be that this is like in a pattern of like plus, plus, minus, minus, plus, plus, minus, minus. That's not truly alternating, but that series would converge if the positive version converges. The converse is not true. So here's my example. Here's an alternating series from 1 to infinity, -1 to the n, that converges. It's just over n. So it's the alternating harmonic series. And that converges because remember, we learned about this in the previous day of notes. If a series is alternating, the terms are decreasing to 0. Well, I guess that's both. The terms are decreasing and they're approaching 0. Then the series converges. So this converges by alternating series test. But just because the alternating version converges doesn't mean the non-alternating converges as well. If you take out the -1 to the n and just make it 1 over n, this is the harmonic series. And we know that the harmonic series diverges. If you need to name a test for that, by the way, it's a p series, right? So you can also just say harmonic series diverges, but technically it's a p series. So this would be a case of conditional convergence. So we have 2 scenarios. If we know that a regular series converges, so the non-alternating converges, and, oh, sorry, I have that backwards. If we know that an alternating series converges, and the absolute value, so the non-alternating converges, then we say that this series is absolutely convergent. It converges whether it's alternating or not. If a series is alternating and it converges, but you look at the positive version of that series, the non-alternating, like I just showed you, harmonic, and that diverges, then that's called conditionally convergent. And we usually use this for alternating series, but again, it doesn't have to be alternating. It's just if you are looking at a series that's not always positive, and that converges, and then also the always positive converges, then that's absolute, or vice versa, it's conditional. So let's take a look at these examples. Determine the convergence or divergence, that's step 1, and then if the series is convergent, classify as conditionally or absolutely. They love to make these parts of free response questions, and it's very likely that part of one of our free response questions on our Chapter 9 test will be about this conditional or absolute convergence. So let's start with this. Anytime I see a -1 to the n, I'm going to check the alternating series test. So these terms would be alternating because they have a -1 to the n. Make sure the terms are going to 0. the limit as n approaches infinity of n factorial over 2 to the n. These are not going to 0. A factorial will beat out an exponential in the long run. So this limit is infinity. So it doesn't mean that it diverges by the alternating series test. It means that the series diverges by the nth term test. Nth term test can be looked at in absolute value, so you don't need to incorporate the -1 piece of it. All right, so we don't worry about conditionally or absolutely if the original alternating one doesn't even converge. All right, so let's go to this one. So this one is alternating. Show the limit. You do have that bit of work to show of the non-alternating series. So these terms in absolute value are approaching 0. And it's true that the terms are decreasing as well. I just show that statement by plugging in n plus 1, again, to the non-alternating version. Show that that's less than 1 over radical n. You don't have to prove this, but it's just true. And then so this converges by alternating series test. You need to show all of that before you go on. So, okay, so that converges. And then we also have to follow up with conditionally or absolutely. So to answer that piece, you check the positive version of this series. When you do this, you need to show the full summation notation. I have students every year that get lazy about this, and they don't write the summation or they don't write the full series. So write the whole thing. Just change this to not alternating. And then this is a divergent P series. That's all the work you have to show. It's because P is 1/2. So you can just say that. And so because the positive version diverges, but the alternating converges, this converges by alternating series test. I'm just going to add the word conditionally. Okay, let's take a look at number 3. If you don't see an obvious -1 to the n, if it's something more complicated than that, you always need to check what's happening with these signs. It's not guaranteed that this is alternating. It could turn out that it's always positive or always negative or just some other pattern. So let's do a quick check on this first. So when n equals 1, I'm just looking at the -1 piece of this. So you get -1 to the 1 times 2 divided by 2. -1 to the 1 is -1. So the first term is negative. Check n equals 2. If you plug in 2, you get -1 to the 2 times 3 divided by 2. That's again -1 to the odd, so you're going to get -1. So this is not alternating. I can't say this converges by alternating series test right off the bat. I want to know if it's always negative, so plug in another one. N equals 3. 3 times 4 over 2. Now this is not odd. This is even, right? This is 3 times 2, which is 6. So that's going to be -1 to the 6th is +1. And I bet if we check 4, it's going to be positive again. -1 to the 4 times 5 over 2. Yeah, that's -1 to the 10th, so that's positive. So this one's going to go minus, minus, plus, plus, minus, minus, plus, plus. And even though that's a pattern, it's not alternating. And it's also not truly geometric. This is kind of a weird one because it's almost geometric. It's got the 3 to the n in the denominator. But if I were to divide terms 2 and 1, I would get that r is positive 1/3. But if I were to divide terms 3 and 2, I would get that r is negative 1/3. So it's not quite geometric. So this is an example of where we're going to rely on that theorem up there. Get back up here to it. We have something that's alternating or something weird, right? It just has, how about we say this, alternating or changes signs. If I can show that the positive version of this series converges, then even if I throw in some positives and negatives here and there, that's going to converge as well. All right, so let's look at the positive version of this. I do know that the series from 1 to infinity of 1 over 3 to the n is a convergent geometric series. And so I don't really have like a test to cite for this, but it's just using this theorem. So it means that therefore this series also converges. And I can still answer conditionally or absolutely. So this series converges, the positive version converges, so it converges absolutely. So kind of a weird case. All right, and then let's take a look at, this is our last example. So again, I see a -1 to the end, so I just want to check to see if this converges first off. So this is alternating. Take the limit as n approaches infinity of the non-alternating expression, so 1 over ln of n plus 1. That is bottom heavy, that's going to go to 0. And are the terms decreasing? Well, 1 over ln of n plus 1 plus 1, or n plus 2, is smaller than 1 over ln of n plus 1. So yeah, the terms are alternating, decreasing to 0. So this series does converge by the alternating series test. Now we just need to answer the conditionally or absolutely piece. And so this one's not quite as clear cut. It's not just like a nice geometric or p series. So we might have to do some work on this. But the first thing you have to do is write the series you're talking about. You don't get credit if you don't write the positive version of this series. So here's what I'm looking at. Running through my list of things. It's not geo. It's not p series. Nth term test, the terms are going to 0, so it's not going to fail that. It's not alternating. If I were to try to integrate this, I can't easily integrate 1 over ln of something if there's not like another n out here. So that's not going to work. So that leaves me to a comparison test. I can compare this to something. And you have a couple of options. I would say 2 options for what to compare this to. Think about function races. This is what I always default to. Natural logs are one of our slowest growing functions that we work with. So you could go to linear, or maybe between linear and natural log is like the square root graph. If you go cube root, cube root will eventually, if you graph it, it'll get lower than the ln graph. So I'm just going to compare it to 1 over n. Again, you could do square root of n if you want, but I usually don't mess with the square roots because I don't know for sure that square root of n is always bigger than ln of n plus 1. I do know that n is going to be bigger than ln of n plus 1. So this fraction here is going to have a bigger denominator. That means it's smaller. So 1 over ln of n plus 1 is going to be bigger overall than 1 over n. And I know about the series that involves 1 over n. So again, you need to write the series with all the notation here. If you only write 1 over n diverges or something, that's going to be wrong. But I know that this is a divergent harmonic. And remember, if the one on the bottom is diverging, then the one on top converges. So I can say by DCT, I can say that the series from 1 to infinity of 1 over ln of n plus 1. I could have put n plus 1 here too, by the way. I just wanted to use a pure harmonic series. Diverges as well. Diverges by DCT. You could also do a limit comparison test if you're not sure on this comparison. But yeah, I don't think we need to in this case. So direct comparison test. And so if the original converges because it's alternating, but the positive version diverges, this converges conditionally. All right, that finishes up this set of notes. I think we only have one more pair of tests to learn tomorrow. So then we'll be done and we'll just practice using all of these when we mix them up.